Awesome. All right, so starting today, we are going to start a more exciting topic on deep neural networks. We're going to use the tools that we have worked on, we have discussed so far, and we're going to use them to build more sophisticated models. So before going there, just as a motivation, why we want to go to deep neural networks. We already worked on, node embedding approaches. We were learning some representations in different levels of a graph for different levels of tasks. But what's the idea behind moving to deep neural network? So there are some problems with the shallow embedding methods that we have studied so far. One problem is that they have an encoder, which is essentially a dictionary lookup. You have, for instance, a graph of V nodes, and then for each of these V nodes, you're directly learning an embedding vector. And your encoder, essentially, its parameters are the embeddings that you're learning directly. So that means that there is no sharing of parameters between basically these different nodes, and for each node you're learning a separate embedding without sharing any of the parameters of your network. That's going to cost us quite a lot when we move to graphs that are pretty large. Maybe they have nodes in the order of hundreds, not hundreds, but tens of thousands, right? There are many graphs in practical applications like social networks or any other type of networks that has too many nodes. We have to have something more convenient that shares some parameters. It also is statistically less efficient because we are not sharing information that we are using to learn embeddings for different nodes, right? So essentially we are learning separately for each node in the graph. Another problem is that these methods are transductive. So what that means is that if you have a graph, let's say that, what that means is that they can only work on whatever they saw during the training, right? So let's say that I have a graph here and I train some shallow embedding methods on this graph, and then that resulted into some embeddings of the nodes of this graph. Now, let's say that I go ahead, add a new basically node to this graph. That can be, for instance, it's a Twitter. And then after we computed embeddings for everyone, now there's a new user, and this new user is following a couple other pages, right? So it is evolving. And then we want to learn embedding for this with the method that we already developed, but it's not possible. We need to go ahead and do some more optimization in order to find some new embedding for this new node. So it can't generalize what it learned during the training to a node that it didn't see before. So it means that it can't be helpful on inductive, essentially, applications. Another problem is that, let's say that you have a graph, let's say that it's molecular graph. There are some attributes associated with each node in this graph, where, for instance, in this example, there are one-hot vectors of the atom types. Now, if you continue this, you have attributes for every node in this graph, and these carry some information that can be useful for generating node embeddings. But using these shallow embeddings, there is no way to integrate this information into your embeddings, because shallow embeddings only look at the index of the node with basically whatever method that you have enumerated that graph. So that's another problem. So you want to basically be able to use this basically graph embedding methods for inductive applications. You want to use node attributes, integrate those into your embeddings, and you also want to use these methods on graphs that are very large. So for these reasons, we need to move on to some more sophisticated models, and that's going to be the deep learning models. So we'll look at some motivations behind where deep learning is coming from. So in many supervised problems, what we want to do is that we want to find basically we have some input X and we are mapping that input X to some output Y, right? That can be a real number, that can be a category. So the idea is that our machine learning model wants to learn this mapping from X to Y. And that can be useful, for instance, for regression problems. We have multiple variables. Let's say that we have some patients and these patients have some vital basically signals. We want to predict some basically from a score for each patient based on his or her vitals. So then this is essentially mapping some numbers to a single real value. Then we can have classification problems where we have basically some image, and then we want to map this image to the correct category that it belongs to. So for instance, here is just cats and dogs. We want to basically get this, we want to map that. So there are some models, linear models that we can use for these. Linear models are essentially you have your input X, you apply a linear transformation on this, and you get some output Y. We show that using a function f parameterized by theta, where theta is just our model parameters, which here in this relation is just our weight and our bias B. So now this is restricting because it only can learn models that are linear, right? So if the inherent mapping between the inputs and outputs are not linear, we won't be able to fit a good model into this data. Another improvement on this is to not to use this directly, this X directly into our linear equation. We apply some transformation of X, we call it phi, and then we plug that phi of X into the linear transformation Wx plus p. So instead of X, we use phi of X. So that's going to give us a basically expansion. We can think about that phi of X as some expansion and some basically basis function and we can think about this equation as expansion of Y into some basically these bases. So it is essentially linear with respect to phi of X. So it is easy to optimize, but there are some problems with this. Because, so one problem is that we need to hand design these fees. We don't really know where these fees are coming from. We need to kind of hand design them so that they give us good mapping, right? We can learn something, some good mapping from X's to Y's. And that depends on the task that you have. So you need some machine learning experts working for years and coming up with, you know, a few transformations phi that we are currently using. And there's no, I mean, there's a few very famous ones because they work really good, but other than that, so you can't really rely on hand designing this one by one. Another problem is that if the dimensionality of our input goes higher and higher, it is going to be harder to use these basically transformations. So one approach now is that to learn this phi. So we want to learn some basically transformation phi. Let's say that we parameterize that with basically some parameter theta. And the idea is that we have some data and we adapt these transformations of X into our data. So let's see how that would look like. We have some equation and then we define a transformation phi theta 2 of X. I call it theta 2 because I call the parameters of our original linear model as theta 1. So now I have the set of parameters for my model includes W, B, and theta 2. So when we train, we have X's, we have Y's, and we want to fit a model basically based off of these three parameters. So now the idea behind neural networks is that in order to be able to model more and more complex mappings between X and Y, we can apply this recursively. Let's say that I have phi of X, I have this Y, I think that this is a new X for another basically transformation. So I repeat that multiple times and I get something that can model something more complicated and more complex. So that's the main idea behind deep neural networks. So we will start with a fully connected feed-forward network, and that's what we really want to basically think about at this point on basically just the networks that work on Euclidean data. So let's say that we have this map from Y to X, we call it f of theta, and this map is essentially a cascade of layers. And these layers, we can show them with the inputs with YL minus 1. We call it a layer L, right? I have the inputs to layer L called YL minus 1. I have the output called YL. We give the input, we apply some essentially transformation on this, and then we apply some nonlinear layer. And basically what we get at the end of the day is basically two sets of parameters that we need to optimize. And then in this equation, we say that our X input is Y0 is our X, our input, our initial input. So we have multiple intermediate layers. We have some input, then multiple intermediate layers, and we have at the end of the day, we have some output for after repeating this for L times. So this is how essentially you can think about this. You have some data, it comes into our network. We apply some nonlinearity, we apply some weight, and then it basically goes until we have some output. We call each of these intermediate layers a hidden layer. And yeah, so we said that we have some nonlinear function, and the reason behind that is, one reason behind that is that if we don't have a linear, basically nonlinearity, what will happen, we can just represent the cascade of our weights as a basically large matrix multiplication of multiple matrices, and we can just represent that as a single linear matrix at the end of the day. So if we don't have nonlinearities, our neural network will be equal to some basically linear transformation only. There are multiple type of basically nonlinear networks, nonlinear layers. We call them activation functions. It's basically same basically work used for nonlinear layers in the neural network. And there are a given number of these. You can, technically speaking, write your own function and use it, but there are a given number of these that basically are in use. In the beginning, people were using this hyperbolic tangent function really a lot, and that gets some input X and returns some value between -1 and 1. It will scale your value in that range. There is a similar function, sigmoid, which gets basically data and returns some value between 0 and 1 again. Between 0 and 1. So it is, the other one was between -1 and 1. There are some problems with this, and the problem is that gradient, we will touch upon this later, but just briefly, these functions saturate when we go to -n plus infinity. What that means is that they're just a straight line. They're the gradient of, basically the derivative of this function with respect to our X variable is going to be 0. And then when our optimization model wants to optimize and find the best parameters, that will give you a 0 gradient, and your optimization model won't be able to basically go search for a good solution. So that's one problem with this. So people are now the most basically prevalent nonlinear layer is ReLU, which is essentially defined as a maximum of 0 and X. So you gave your X, if it's negative, it's just going to be 0. If it's positive, you're going to get the same number. Now, This also sometimes saturates when the output basically the input falls into these regions, and we call that a dead value because it's not gonna get updated anymore. It doesn't happen all the time, but if it happens in some application, instead we use leaky value. The idea of that is that we have a small slope, which is not zero, but it's very close to zero. So we won't have that dead value problem anymore here. So this is basically another function that people use. It is not as popular as value, but in some application we need these. Another nonlinear layer that I have used a lot personally is soft plus. This is essentially a smooth version of the value. And that means that it doesn't have that angle here around zero. One application of this is, for instance, in meta learning, when you have two optimization loops. Basically, you want this function that you write be double differentiable, so you don't really want some angle in your nonlinear layer.